Hello everybody and welcome to a session where we are going to look at some problems in electromagnetism. Specifically, we'll look at the problems of electric field and capacitors. So let's look at the first problem. So here is the statement of the first problem. Two spheres of electric charge plus 2 nanocoulomb and minus 8 nanocoulomb are placed at a distance d apart. If they are allowed to touch each other, what is the new distance between them to get a repulsive force of the same magnitude as before? So now if you look at this question, we have two spheres touching each other and they carry different charges. So what is going to happen? And second part is the magnitude of the force between them. Now let's look at the first part where we have two spheres of different charges touching each other. So one sphere has minus 8 nanocoulomb, other one has plus 2 nanocoulomb. So if they touch each other, the total charge will be plus 2 nanocoulomb and minus 8 nanocoulomb, it will be minus 6 nanocoulomb. Now this minus 6 nanocoulomb charge will be separated equally on or distributed equally on those two spheres. So this is the answer to the first part of this problem. Now how do we find the repulsive force? Now let's look at the important thing, which is the magnitude. So let's first write down the magnitude of the force. Let's not worry about the direction of the force, where it's attractive or repulsive. So we can write the magnitude of Coulomb force between two charges Q1 and Q2 that are separated by distance r. So this is the general expression for the force between two charges. Now let's apply this to these two cases. So here is the first case where we have plus 2 and minus 8 nanocoulomb. Now let's not worry about the sign, because since we are interested in magnitude, so we have just written down the magnitude of the charges over d square. So this is the magnitude of the force. In the second case, when minus 3 will be on one sphere, minus 3 on the other sphere, we will have the magnitude of the force will be this Q1 Q2 over x square. Now we assume that x is the distance between those two spheres. Okay, now the question says that these two magnitudes f1 and f2 should be same. So when we equate this, this 1 over 4 pi epsilon factor will go away, and the minus 10 raised to minus 9 factor in both these cases will also go away. So we will get 16 over d square on the left hand side and 9 over x square on the right hand side. So if we solve for x, we get x equal to 3d by 4. So this is the answer for the first problem. Let's look at the second problem, and the statement is 4 into 10 raised to 10 electrons are removed from a neutral metal sphere of diameter 20 centimeter placed in air. The magnitude of the electric field, which they are asking, is in Newton per Coulomb at a distance of 20 centimeter from the center is. Okay, now what we need to do is we need to solve this first and using Gauss law, because if you remember, we can use Gauss law to find the electric field coming out of a Gaussian surface. Okay, and whatever charge enclosed within that sphere, the electric field is proportional to that charge. Now we are exactly at a distance of 20 centimeter. Now most of the charge if you remove charge from the metal, it will get positively charged, and most of the charge will remain on the surface of the sphere. It won't be inside. Okay, so since we want to calculate this, we can consider that this charge which is on the surface of the sphere is inside this and considered at the center of the metal sphere. So using this, we can write down the expression for the magnet of electric field due to charge q at a distance r. E is equal to 4 over 4 pi epsilon naught into q over r square, where q is the charge at the center, and we can assume that this is the charge, which is these many electrons times charge of electron is the total charge. So we can calculate this quantity electric field using this expression. So let's do this exercise. So 1 over 4 pi epsilon naught is 8.99 into 10 raised to 9 Newton meter square per coulomb square. These many number of electrons, okay, and this is the charge of a single electron, and R is 20 centimeter, which we have now written in meter. Okay, so what we can do is 10 plus 10 minus 19 will be minus 9. Minus 9 and this minus 9 will go away. So we need not worry about power of 10. Only thing we need to now write down is this expression 8.99 into 4 into 1.602, and we can write down this square, because this will be now 0.02 square is 0.04. Now this 4 will also go away, so we will be left with a factor of 10 raised to 2. So you can have our final thing here that you need to calculate is 899 into 1.602. So if you do that, then we end up with this magnitude for the electric field. Let's look at the next problem, and the statement is 2-point charges. One is of 3 nanocoulomb, other one is of 1 nanocoulomb, are placed 5 centimeter apart in air. The work done to move charge V towards A by 1 centimeter is. So now in this problem, we need to calculate what is the work done if you move charge B towards charge A. And let's write down the expression for the work done due to moving charge Q. And this is the expression. So Q is the charge, Vi is the potential at the initial position of the charge, and Vf is the potential at the final position of the charge. So now we are moving charge B, so I just write down this QB. Now potential at the initial position, if you recall the expression for the potential due to charge is charge over 4 pi epsilon naught times the distance Ri. So Ri is the initial position, Rf is the final position. So this gives us the potential at the final position. So now to calculate this quantity, the work done, we need to plug in the values and solve for this expression. So let's do this. So here the work done is QA QB over 4 pi epsilon naught, and I'll get this factor. So 1 over 4 pi epsilon naught is 8.99 into 10 raised to 9 Newton meter square per coulomb square, and this is the magnitude of charge A, this is the magnitude of charge B, and now I have 1 over 5 centimeter, which I converted into meters, and this is also 1 over 4 into 10 raised to minus 2 meters. So we can simplify this minus 9 and plus 9 will go away, this minus 9 and this minus 2, if you bring minus 2 up, it will be minus 7, so I can bring out this factor. And now I need to do this calculation, 8.99 into 3, and this 1 over 5 minus 1 over 4. Now 1 over 5 is 0.2, 1 over 4 is 0.25, so we get minus 0.5. If you do this calculation, then we get this as minus 1.35 into 10 raised to minus 7. Here the negative sign indicates that we are moving from a lower potential to a higher potential, and this is quite obvious since we are moving closer to a positive charge. Okay, so this is what is indicated by this negative sign. Let's look at the next problem. So the statement is a system of two capacitors of capacitance 2 microfarad and 4 microfarad is connected in series across a potential difference of 6 volt. The electric charge and energy stored in the system are. So first thing that we need to do is to calculate the effective capacitance, and for the capacitors which are connected in series, this expression gives us the effective capacitance. So if we plug in the values in this expression, we get 1 over C is equal to 3 over 4 microfarad. So C is equal to 4 by 3 microfarad. So now to calculate the charge stored, you use this expression Q is equal to CV, which gives us 8 microcoulomb. Now if you recall the options we had earlier, only one option had 8 microcoulomb. So you can choose that option. Nevertheless, we can confirm it by calculating the energy stored, which is equal to 1/2 CV square. So this, if you plug in the values, we get the energy stored as 24 microjoules. Let's look at the next problem. The minimum value of effective capacitance that can be obtained by combining 3 capacitors of capacitance 1 picofarad, 2 picofarad and 4 picofarad is. Now the important thing is we need to find out the minimum value. Now if you connect the capacitors parallel, these 3 values will be added up. So now if you connect them in series, then we will have addition of the inverse, which is what is shown here. So we get the minimum value when we connect them in series. So if you just plug in the values, we get C is equal to 4 by 7 picofarad. Let's look at the next problem. A mass of 1 kilogram carrying a charge of 2 coulomb is accelerated through a potential of 1 volt. The velocity acquired by it is, okay, so now this has to do with the conservation of energy. Okay, from the conservation of energy, Ki is the initial kinetic energy, Ui is the initial potential energy, and this is the final kinetic energy and final potential energy. So the change in the kinetic energy is equal to change in the potential energy. Now here we take the initial kinetic energy as 0, so 1/2 mva square vf square. This is the final kinetic energy is equal to. Now this is the change in the potential energy, which is equal to Q into delta V, where delta V is the change in the potential. Now here we are seeing that the charge is accelerated through potential of 1 volt. So delta V is 1 volt. So we rearrange this equation. So we get Vf is equal to square root of 2Q delta V over M. And if you plug in the values, we get the final velocity as 2 meter per second.